Okay, we're back for part 6. We're in the home stretch, only this one and one more to go on Unit 13, talking about acids and bases. Same objectives still. We're still looking at all this good stuff. If you need to read it, pause and feel free to read. We're going to talk some about the pH scale, where it comes from, what it means. It's a little bit confusing, and there's a little bit of math that we're really not going to get into in this video, but we will get into in class. So, just be ready for that. It's fun stuff. pH. First of all, the H part comes from hydrogen ion. Okay? It stands for the negative logarithm of hydrogen ion concentration in a solution. Now, I did use a strange word there, logarithm. We'll come back to that here in just a little bit. Don't be scared. Hydrogen ions in water. And if you remember, for acids, when a hydrogen ion gets put into water, remember, it grabs onto those water molecules and it turns it into hydronium ions. So again, you can use hydronium concentration, hydrogen ion concentration, pretty much interchangeably here. Now here's the thing. Remember, we talked about the fact that water is an amphoteric substance, meaning it can be an acid or it can be a base. Well, something else weird about water is that water self-ionizes. Water can dissolve itself. You can have water molecules just randomly floating there, and all of a sudden one of them comes apart into a hydrogen ion and a hydroxide ion. So it becomes just automatically both an acid and a base. Well, usually what happens is that they suck back together again and it turns back into water. But at least for part of the time that water exists, it exists as hydrogen ion and as hydroxide ion. So you can say at any given time you've got a concentration of hydrogen ions and hydroxide ions in any given sample of water. And if it's pure water, then its hydrogen ion concentration is equal to 1 times 10 to the negative 7th moles per liter. Also, its hydroxide concentration, because remember, for every hydrogen it makes a hydroxide. Its hydroxide concentration is also 1 times 10 to the negative 7th moles per liter. Now, I want you to notice something. You see this little 7 right here? That's going to be very important. We're going to come back to that here in just a minute. But before we get off of this, if you take this number and you write it out, we're talking about a 1 with 7 zeros in front of it and a decimal. Okay? So we're talking a very, very, very small concentration of either hydrogen or hydroxide here. That decimal is way out there to the 7. Same thing, all acids, whenever you put them in water, they make hydrogen ions. All bases, you end up getting hydroxide ions. But here's the funny thing, that even in acidic solution, you've still got some hydroxides floating around in there. You don't have very many, but you have some. And even in a base solution, you've got some hydrogen ions floating around in there. Again, it's really low, but they do exist. I know this is just kind of strange, mind-blowing stuff. Now, if something has a pH of 3, remember, any pH between 7 and 0 is acidic. If something has a pH of 3, it means that its hydrogen concentration is 1 times 10 to the negative 3 moles per liter. Now wait a minute, you see this pH of 3 right here? You see it's 1 times 10 to the minus 3. Do you think those are connected? Spoiler, they're totally connected. Because some guy named Soren Sorensen, and I don't know where these guys get their awesome chemistry names, but you got Svante Arrhenius, you got Soren Sorensen, I think probably, I think Gay-Lussac is probably my all-time favorite cool chemistry name, but I'm sorry, I'm getting off track here. Soren Sorensen decided, that's hard to say, that it's a lot easier to say pH of 3 than it is to say hydrogen concentration of 1 times 10 to the negative 3. Okay, really, really smart guy. And so we use the pH system to take these big, long decimal concentrations and shrink them into a smaller number. Now here's the thing. Because this is 10 to the negative 3, and we saw a minute ago water was 10 to the negative 7, that means that for each little place here, each little exponent here, you're going out or you're going in another decimal place, which means every step away on the pH scale, say from pH 3 to pH 4, we're talking about a difference, a factor of 10. It's either 10 times more powerful or 10 times weaker. Okay? This is what's called a logarithmic scale. So here's the pH scale. That was fancy. Acids are anything from 0 to 7. Bases are anything from 7 up to 14. 7 itself is neutral. And like I said, each step is a factor of 10. So if I've got something that's pH 5 and pH 6, the pH 5 is 10 times more acidic, has 10 times more hydronium or hydrogen concentration than the pH 6 did. And if I've got something out here at pH 3, that's 2 steps away. Well, here's a factor of 10. Here's another factor of 10. What's 10 times 10? Absolutely, which means that something that has a pH of 3 is 100 times more acidic than something that has a pH of 5. And it gets even better. The further away, you just keep adding another factor of 10. So 1,000 times, 10,000 times, 1,000,000 times more acidic. And it looks like it's just a very small difference in numbers. It's really a huge difference in that hydrogen concentration, okay, in how acidic that acid is. Look at 8 versus 13. Oh, yeah, I'll let you look at 8 versus 13. Now, 8 versus 13, how many steps away are we? 1, 2, 3, 4, 5. That means it's 10 times 10 times 10 times 10 times 10 as far as the difference in pH. I'll let you do the math on that. Okay, here's the pH scale and a really big, pretty kind of pixely chart. Of course, here in the middle you've got neutral. This is where you normally have, water. Sometimes it can be slightly acidic or slightly basic. Going up from acidic, this right here is where most snow and rain and stuff, it's slightly acidic. Going a bit more up here, you start getting into acid rain around a pH of 5 or 4 or 3. Fish start dying. Then you get vinegar, lemon juice, battery acid. Battery acid is really pretty strong stuff. That's why you don't want to mess with car batteries. Dropping down, I say dropping down, it's actually getting higher on the pH scale. You start getting into basic things, okay? Baking soda is right around pH of 8. Milk of magnesia is down here by 10. Household ammonia. Lye, remember lye, sodium hydroxide, very, very strong base, very dangerous stuff. Oh, I totally forgot. Way back in video number 1, I talked about the fact that bases have a slippery feel when you touch them. The reason bases have a slippery feel is because they're dissolving the outer layers of your skin. And so it's actually decreasing the friction because your skin is dissolving off. Isn't that fun? You can measure pH in a bunch of different ways. Why would you want to know the pH of something if you weren't in a chemistry class? Well, where do you hear about pH when you're not in a chemistry class? That would be things like swimming pools or aquariums. Okay, if you're going to keep fish, you need to keep fish at a certain pH, or you saw in that last slide they die. You need to make sure that the chemicals that you bring in contact with your body are of a certain pH, because if something's too basic, then instead of just washing your hair, it can actually dissolve your hair. Number of different reasons. And you can test using indicators. And you don't have to go into chemistry class and get an indicator. You can buy these things right off the shelf. Pretty much, I'm pretty sure you can find these in Walmart. Okay? Indicators, remember, are compounds that colors change whenever they're exposed to acids or bases. Here's several different indicators, and these are the different pH ranges that they measure. Gosh, I'm not even going to try and read all those off, but yeah, there's lots and lots of indicators. It's not just litmus, it's not just phenolphthalein. You can use pH paper, and if we get a chance to, we're going to be doing a lab where you're going to be measuring the pH of several different substances using pH test paper. The way you do that is you take your paper, you dip a glass stirring rod into whatever you're going to be measuring, you touch the glass rod to the paper to get a drop or two on there, and you very quickly note if there's any color change. And then you look on the little package of paper, you see what your color is closest to, and that can help you to figure out what the pH of your solution is. Of course, there's a bunch of other ways to measure pH besides using paper. You can use these little electronic pH meters, these big electronic pH meters. They sell little pH test kits whenever you have swimming pool supplies. Lots of different ways, if you really want to know the pH of something, for you to figure it out. And that's the end of video 6. Only one more to go. Stay tuned.